Today it's going to be Newton and Newtonian Worldview. Now you have to understand that Newton and his position in the 18th century, 19th century was something exceptional in the history of science. He was revered to such a degree that probably no other scientist has ever been revered. When he died in 1727, a famous English poet, Alexander Pope, wrote a famous epitaph on Newton. It goes like this: Nature and nature's laws lay hid in night. God said, let Newton be, and all was light. It wasn't only Pope's opinion, it was commonplace. He was compared to the biblical Moses. Because you see, it was believed that God gave Moses the laws of morality, the laws of behavior, and to Newton, he gave the laws of nature. And you have a nice parallel here. You have Moses and you have Newton. As a result of this, you can imagine that he was given a semi-divine status. And what often happens, this gets exaggerated. This whole process started while he was alive. I'm going to give you a few 18th century engravings. This one is from 1711, and on this engraving, you have Isaac Newton here as a source of light and knowledge. This one is probably one of the most famous engravings. This one is from the book by this guy here, by Voltaire. This is 1738. Now you see the divine light of knowledge shines through Newton, this is Newton, and is reflected to Voltaire, who writes everything down because he presents the principles of the Newtonian philosophy. Here's another one. So another engraving from another frontispiece. Here Newton is portrayed as the goddess of wisdom. Why goddess? I have no idea. Now, the goddess of wisdom, Minerva, and you see she holds Newtonian drawings. They're all over the place. So there you have it. Newton, the divine Newton. And as a result of this, he and his worldview, they have been ascribed many things that have nothing to do with either Newton or the Newtonian worldview. This is what always happens, right, when you keep exaggerating things. These 5 that I'm going to give you are among the most famous myths on Newton and Newtonian science. Here's the first one. Newtonian science liberated itself from religion. Number 2, Newtonian science completely rejected astrology. Number 3, Newtonian science united terrestrial and celestial physics. Number 4, Newtonian science opened up the closed, the finite universe. It made the universe infinite. And finally, number 5, Newtonian science was the first to employ the scientific method. And you know what they mean when they say the scientific method. They mean the contemporary one. Now tell me, any of this hold water? At this stage, you have enough knowledge to tell me why the last one is incorrect.
My name is William Wilson. Because there were other scientific methods before the hypothetical deductive method.
That is true. But if we focus on the hypothetical deductive method itself, would this be true?
Didn't Descartes use it?
Very good. Hypothetical deductive method was part, or had been part, of the Cartesian mosaic long before Newton. So you can't say Newton was the first to employ that method. Now let's consider the other ones. What about the rest? Newtonian worldview? Newtonian mosaic was accepted until around 1920. In Britain, it was accepted since around 1700, you know this, and on the continent, it was accepted since around 1740s. There is an exception to this. We have new data showing that some parts of the Newtonian worldview had been accepted on the continent since around the 1720s, in particular in Dutch Republic. By the way, it needs to be said that this mosaic, by the time it got replaced by the contemporary worldview, general relativity and other things, it had undergone so many transitions that the Newtonian mosaic, the early 20th century, had very little in common with the Newtonian mosaic of the 1800s. The reason why we present this as a single worldview is that they shared the same fundamental assumptions, but specific theories were quite different. By the early 20th century, you wouldn't have many of these theories. Now, what are the elements of this mosaic? In the center, you have Newtonian physics, then you have phlogiston chemistry, Then you have the theory of preformation, linear and biology, physiology, some psychology, history, mathematics, hypothetical deductive method, Keplerian astronomy, and then you have theology, which should be really surprising to people who believe that Newtonian science liberated itself from religion. Yes, this is how it liberated itself from religion, by having theology in the most visible place. How do we know this? There's certain evidence for that. I'm going to give you a hint as to how historians study these things. First things first, the definition. What is theology? Theology is the study of God and the relations between God, mankind, and the universe. It was believed that there are two types of theology. One is called revealed theology. This is the branch of theology that's concerned with inferring God's existence and attributes exclusively from God's act of self-revelation. So essentially, this is that theology that is based on holy texts, supposed acts of self-revelation. And here you have natural theology. Now this is the branch of theology that's concerned with inferring God's existence and attributes by means of reason, unaided by God's acts of self-revelation. So when people like Descartes and others try to infer God's existence and his attributes, not from the holy text, but independent of cases of revelation, when you try to say something about God by studying the world around you, that would be an instance of natural theology. And now you can say, Hakob, but how do you know that any of this was part of the mosaic? Well, we have reasons to believe. There are textbooks, there are university curricula, and there are encyclopedias. Luckily, the 18th century gave us two big encyclopedias. There's the French encyclopedia, and there is Encyclopedia Britannica. And I'm going to give you the French one. Here we have the system of human sciences, divided based on our three major faculties: mémoire, raison, imagination. Memory, reason, imagination. Now, in imagination, you have all sorts of literature here, you see. In memory, you have history, natural history, social history. We are interested in this one, reason. And here you have theology, science of God, among other things, among natural sciences, humanities, metaphysics. If I zoom in here, then immediately what do you see? Théologie naturelle, théologie révélée. Natural theology, revealed theology. They were both part of the science of the time. Now, this classification, just for your future reference, includes not only things that were accepted, but also things that were rejected. So this gives you an overall classification of everything that human beings do. So you have to refer to their individual articles within the encyclopedia to actually see how these supposed branches of science were actually treated. And if you refer to individual articles, it becomes obvious that both natural theology and revealed theology remained in the mosaic. What was never accepted is this thing here, divination and black magic. Divination, magie noire, was never accepted. Even in the Aristotelian worldview, this was never part of the mainstream science. So in terms of exiling theology from the mosaic, it did happen, but it happened only in the 20th century. In some cases, it happened in the 19th century, but not in the 18th century. Okay? So you can't say that Newtonian science liberated itself from religion. No. Theology continued to remain part of that science for a very good chunk of time. All right, now what about astrology? Again, let's continue with the same diagram. If we look at the bottom of that diagram, among physical sciences here, you see zoology, you see meteorology, cosmology, botany, mineralogy, and then you see astronomie physique, physical astronomy. And there you also have astrology. And here you have judicial astrology and natural astrology, physical astrology, two different branches, and I have to explain this. Astrology here, the science concerned with influences of the stars and planets upon terrestrial affairs. Natural astrology is that branch of astrology that studies the celestial influences upon natural things. And judicial astrology would be a branch of astrology that is concerned with celestial influence upon human affairs, everything that involves human mind. So here in this branch, you would have things like measurement of time, weather forecast, prediction of tides and eclipses, medical prognostication, so everything that has to do with material stuff. anything that doesn't involve human mind. And here you have predictions on the individual's life and character, nativities, individual horoscopes. Okay, this is a good week for you, this is a bad week for you. So those things would be part of judicial astrology. Social, economic, political forecasts, so anything that has to do with human beings and human affairs. Even in medieval science, only natural astrology was accepted as part of science. Judicial astrology was not part of science. It was considered heresy, because the moment you accept that human beings are free to act the way they want, then any sort of a prediction on human affairs would be in opposition to Christian faith. You understand the consequences here? Okay? Now, what happened to astrology in Newtonian science? Judicial astrology, yes, it remained rejected, and at the time it became subject of ridicule. But this one here, it remained in the mosaic, but something interesting happened. The name astrology was removed. It became part of physical science. So towards the end of the 18th century, you no longer see the name astrology. In the French encyclopedia, it still exists, but then towards the end of the century, it's gone. Encyclopedia Britannica, that was published about 16 years later, so you have 1755, that's your French encyclopedia, and then you have 1771, that's your first edition of Encyclopedia Britannica. In Encyclopedia Britannica, the article on astrology is only 5 lines long, and it says, well, it's been long rejected and it's subject of ridicule. Essentially, they are referring to judicial astrology. But all these things, they remain part of science. It's just they were absorbed by physical science. You see what happened? So you can't really say that astrology was rejected. Many of the problems that astrology studied remain part of science. The name astrology, yes, it was gone. Towards the end of the century, you no longer had astrology. So can we say that this is not good? All in favor? Now what about the rest? Newtonian science united terrestrial and celestial physics. This is one of the first things you learn when you study popular history of science. They say, well, before Newton, there were 2 physics, one for the terrestrial region and another one for the movement of the celestial bodies. So you had 2 different sets of laws, one for the terrestrial events and another one for the movement of stars. And then Newton came and he united the 2. And he gave us one physics that was good enough for both the terrestrial region and the celestial region. Let's see if this makes any sense. We have to start from our Greek friend here, Aristotle, and his universe. In his universe, you see the sublunar region here. Things are made of the 4 terrestrial elements, which either tend towards the center of the universe or towards the periphery of the terrestrial region. And you have a certain set of laws. We've covered these laws. On the other hand, the celestial region here is made of element ether, which tends to move, as you can see, in circles around the center of the universe. So the 2 regions obey completely different sets of laws. The laws that work here are not applicable to the phenomena up there. There is no violent motion up there. There is no tendency to descend anywhere. There is no tendency to ascend anywhere. The only tendency that there is up there is to revolve in circles around the center of the universe. This is the idea of heterogeneity, the idea that different regions of the universe obey different laws. Now, what about the idea of opening up the universe? It is true that the Aristotelian universe was a closed universe. Here, the universe is finite. You see, this is the actual physical boundary of the universe. And this is the conception of finite universe. The universe has physical boundaries. It's finite in space. If you ask Newton, he would say a space exists independently from material processes, you see? It's something in which material objects exist. It's a stage on which you have your material world with all the material objects in it. And this is the conception of absolute space. The space is independent of material objects, that it is an empty receptacle in which physical processes take place. It's not material, it's something independent of matter. It's just this emptiness in which matter exists. If you accept this as your physical conception of space, space as independent void, since it is essentially void, then you cannot possibly think of boundaries in space. But since space is void, the universe must have no physical boundaries. It is infinite in space. Like that. You see, this is our solar system and these are other systems. Right. Now what about the homogeneity or heterogeneity? For this we have to refer to Newton's laws. And here are the laws. The first law, the second law, the third law, the law of gravity. Don't worry, I'm not going to read them. Let's start with the second law. This is what it says. The acceleration of a body is directly proportional to the net force acting on the body and is inversely proportional to the mass of the body. So you have an experimental situation, cannon and a cannonball. This is how this whole situation is analyzed in Newtonian physics. You have an object with a certain mass, and then you have applied force. And this would be the acceleration in this direction, which would be proportional to the force and inversely proportional to the mass. This is very straightforward. Now, what happens when there is no applied force? For that you have the first law. The first law says, if an object experiences no net force, then the velocity of the object is constant. It is either at rest or moves in a straight line with constant speed. So it has to maintain its state, whatever that state is. So in this particular case, if there were no other forces in play here, you would have something like this. So there's no force, therefore acceleration must also be zero. So if there were no forces acting on the cannonball, it would continue to move along a straight line due to inertia. It would kill Newton, essentially, I think. But luckily, inertia is not the only factor here. There are other forces in play. What are those forces? Gravity. Law of gravity. Any two bodies attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. So here in this particular case, you have a cannonball, a certain mass, and then you have the Earth, also with a certain mass. This here would be the distance between their respective centers. The law says that between any two objects, in this case the cannonball and the Earth, there is a force of gravity that is proportional to the product of the two masses and inversely proportional to the square of the distance between them. Now, you zoom out, and this is what you're going to get. In this particular situation, you have two main factors. The first one is inertia by the first law in this direction, and the second one is gravity, like that. So you have two factors. The resulting trajectory will be the combination of these two factors, according to Newton. Again, in this situation, everything repeats. You have inertia, you have gravity, and this would be the combination. So it will end up here. Again, in this situation, similar, similar. So as a result of that, you see that the trajectory of a projectile is a parabola. Now, would these laws be also applicable to celestial affairs? Of course they would be. The same laws that govern the trajectory of a projectile on the Earth also govern the motion of planets and stars. Let's consider one. You have a very simplistic system, a star and a planet, let's say the Sun and the Earth. If there were no force of gravity, what would happen? Well, a planet would continue to move along a straight line due to inertia and would eventually disappear if there were no gravity. But since there is gravity, says Newton, you have two factors. Again, you have inertia and then you have gravity. That's why the resulting trajectory is the combination of the two. So it ends up here. Again, the situation repeats. You have certain inertia, you have gravity, and it ends up here. Again, it repeats itself, repeats, and as a result of this, you get an ellipse. The actual trajectory must be an ellipse. So the laws of nature are the same everywhere in the universe. And this is the conception of homogeneous universe. Pay attention in literature. Sometimes when they talk about homogeneity, they mean a type of stuff of which universe is made. And this is not what we're talking about. We're talking about the laws that govern changes in different regions of the universe, okay? You can subscribe to the conception of homogeneous universe in terms of the laws, but still believe that the universe is made of different things in different regions, the different types of particles in different regions. So it's not the types of particles we're discussing here. We're talking about the laws. So in terms of laws, this worldview supports the position of homogeneous universe. One set of laws for everything in the universe. Right. So there you have it. Your Aristotelian medieval, your Newtonian, finite universe here, infinite universe there, heterogeneity here, homogeneity there. Looks very smooth and nice. And Newton and Newtonian science was the first to open up the universe and the first to unite terrestrial and celestial physics. What's wrong here? You know enough history of science to challenge this view. What about Descartes and Cartesian worldview? He would say, except that it was I who opened up the universe, and it was I who made it homogeneous long before Newton. Let's have a look. Infinite universe, homogeneity, and Descartes' basic idea that matter is extension. Descartes says, any spatial boundary assumes that there is space beyond it. But space is the attribute of matter. It cannot exist independently of matter. Therefore, there is always matter beyond any boundary. If you say that this is the boundary, immediately a question arises, what's beyond it? If it is a boundary, then you remove it, what's beyond it? You can't say nothing. In Descartes' case, you can't have empty space at all. It should be filled with matter, because space cannot exist independent of matter. You remember that? So he says, well, there's no such thing as limits to space. He doesn't use the word infinite, but he says space is extended indefinitely, meaning potentially infinite. And we cannot possibly think of a physical boundary. And this is enough. This gives you the conception of infinite universe. What about this one? Homogeneity. Yes, he did believe that there were three types of corpuscles, three types of particles. And yet he believed that all three types of particles obeyed the same laws, the same basic laws. The first law, the second law, you remember we covered those laws last time. They all obey the same set of laws according to Descartes. And this is what's important, okay? This is what gives you a homogeneous universe. So there you have it. Cartesian universe, again the same diagram, the sun in the center of its own vortex. You have other stars with their own vortices with planets. The universe is extended indefinitely, and all matter obeys the same set of laws. So these two myths are also debunked. So one source of these myths is the habitual neglect of Cartesian science. So this is your usual picture that you get from popular literature. But in reality, you have to do this. And you have to make room for Descartes and Cartesian worldview. Once you do that, you realize that the Cartesian worldview was the first to open up the universe. And it was the first to unite terrestrial and celestial physics. At this point, you might be thinking, okay, what are the key characteristics of the Newtonian worldview? So far, it's very similar to Descartes' worldview, to the Cartesian worldview. So what's so different about it? One conception that both Aristotle and Descartes shared and Newton rejected was that of Plenism, the conception that there can be no empty space. I'm going to explain this. Start with Aristotle, Aristotelian law of violent motion. This is the law. If the force is greater than the resistance, then the object will move with a velocity proportional to the force and inversely proportional to the resistance. If the resistance here is greater than the force, the object won't move. We've covered this. Now you tell me what would happen with the velocity if there were no resistance. What would happen to the velocity in this universe if the resistance were zero?
You'd have a division by zero, so it would either not make sense or your velocity would just become infinite. Infinite velocity, that's what would happen. Thank you very much. When the resistance is zero, it follows from this law that the object would move with an infinite velocity. You know what infinite velocity means? Essentially it means two different places at the same time. Not just two different places, as many places as you wish at the same time. Aristotelians, they understood perfectly well that the notion of infinite velocity is utter absurd. There's no such thing, there can never be such thing, because you cannot possibly conceive of a thing in two places at the same time. Therefore, velocity is never infinite. It just doesn't make any sense. You put these two together, what is the conclusion that follows? Duygu?
Hi. So there is always resistance, at least the air resistance or something?
Perfect. There is always some resistance. Resistance is never zero, which means the medium should always be filled with something. You can never have absolute emptiness. Otherwise, you'd give a little touch, a little push, and it would just disappear immediately. Well, what the hell is this? It follows from this that there can be no empty space, no space devoid of matter, and this is the conception of plenism. Is this clear how Aristotelians arrive at plenism? Very good. And what about Descartes? Plenism was one of very few ideas that they shared with Aristotle. You remember Descartes' deduction, we covered this last time. It follows from the idea that the principal attribute of matter is extension, and we also know that attribute or property needs a substance. You can never have free-floating attributes. You can never have extension without actually something being extended. So when there is no matter, there is no space. And this is where it becomes very interesting, because this is where Newton enters the picture. By the time Newton sat down to write his masterpiece, and we're talking the 1680s, towards the end of the 17th century, there had been several experiments allegedly proving the existence of vacuum. Guys like Torricelli and Pascal already seemingly proved the existence of a vacuum. And this is the famous experiment with the tube of mercury, never repeated at home. It's very dangerous. Actually, people back then didn't know it was dangerous. So what do, you take a tube, closed at one side, you fill the tube with mercury, close it with your finger. This is when it gets dangerous, don't do that. Then you turn it upside down, like that, and you place it in a reservoir with more mercury, like this. This is already upside down, okay? What you immediately notice is a tiny gap that emerges at the top of the column. And this gap, it was argued, is nothing but emptiness, vacuum. This was something that people debated about. It was by no means accepted at the time. The Aristotelian community of the time gave it a very nice explanation. So the interpretation of this as a vacuum was by no means accepted. But Newton thought that those guys, Torricelli and Pascal, they were right in arguing that this is really a vacuum. And therefore, since vacuum exists, then you have to have such physics that makes it possible. So for Newton, the situation was this. Experimentally, it has been shown that vacuum can exist. You can have an empty space. What is vacuum? Vacuum is just space devoid of matter. Therefore, you have to modify your physics such that it allows for the existence of a vacuum. And therefore, he starts from this basic idea that space is something independent of matter, is not an attribute. So the Cartesian definition of space as extension just doesn't make any sense. You have to redefine things. He says space is the stage for material processes. Material objects exist in space. And from this it follows that there can be space absolutely devoid of matter, vacuum, and the conception is called vacuism. You have to think of space as something that can exist even if there is nothing material in the universe. And there's a nice thought experiment. It says if matter disappeared from the universe, empty stage would remain. Descartes would say, if I were alive, I'd say you don't seem to understand, because how can an attribute exist without its substance? What are you saying? How can you ever conceive of the redness in a free-floating state? How can you conceive of extension in a free-floating state? It's not really possible. There can be no empty space, and in reality, extension is an attribute. It cannot exist independently, so it's just a property of material things, like that. If matter disappeared, according to this view, the Cartesian view, what would happen to space? It would disappear too. You would never have emptiness without matter. It should be like this, nothing remains. So this is what you're supposed to see if Descartes were right. Empty space is a contradiction in terms. But Newton would say, I don't care about your definition. Maybe the problem is with your definitions. What I know is that the existence of a vacuum is an experimental fact. It has been established. So you have to change your definitions. You have to start with this one. The space is independent of material objects. Is this clear where they stand, the different parties? Okay, let's sum it up now. It's plenism here, plenism there, and vacuism here. What were the other differences between the two? Descartes again. Action by contact. Changes in material objects can result only from actual contact. Material particles can only interact by colliding with each other. Just like in this case, a material object changes its state only when it is in contact with other objects. This is a genuine drawing from Descartes' book. There's another one. The moon is carried around the Earth by the particles of the Earth's vortex and reflexes everything. Everything is action by contact. Among other things, Descartes' first law followed from it, that every part of matter maintains its state unless a collision with another part changes that state. And you would say, well, this is very similar to Newton's first law, isn't it? Very, very similar to the law of inertia. This one. Every part of matter maintains its state unless it is compelled to change its state by some force. Can you tell me what the difference is? Yep, Miriam?
Descartes' law doesn't take into account gravity as a force.
Okay, as opposed to?
As opposed to actual contact, because gravity is not a force that acts through direct contact.
Essentially, yes. There is an important difference. In Newton's theory, as you can see, changes are initiated not only by collisions, but also by forces. You should not necessarily touch in order to cause something to change in a Newtonian worldview. For Descartes, you don't have a choice. You have to touch, you have to push, you have to collide. In the Newtonian worldview, it can be forces. It's a world full of forces, and this is one of the reasons why the Newtonian worldview was so difficult to digest, specifically by the Cartesians on the continent. I'm going to explain this. In Newton's theory, forces can in principle be applied not only through collisions, but also at a distance. So essentially, this view is compatible with the idea that material objects can affect each other at a distance. One example of a force that acts at a distance, or seemingly acts at a distance, is gravity. Objects pull each other at a distance without any mediators. There is a force of attraction between any two material objects in the universe. Here, the apple and the earth. According to the Newtonian theory, there is no contact. It's just force of gravity acting between the two. The earth and the moon attract each other without any mediating agents. It's not your Cartesian vortex gravity, right? This is a completely different story. If you ask Cartesians, you'll say the idea of action at a distance is occult. It is occult because you can't make any sense of it. It doesn't make any sense whatsoever, and it is similar to the Aristotelian idea of forms. If you define matter as extension, that the primary attribute of matter is extension, then you cannot have action at a distance. Imagine yourself being a Cartesian around 1700s, early 1700s. You are a true, well-educated Cartesian, and then you have this Newtonian theory, and people are trying to convince you that two bits of matter can actually interact at a distance. At least that's what the theory tells you. How would you react? You'd say, well, this doesn't make any sense. We have established that the only quality that matter has is the capacity of occupying space. And this type of matter can never interact with another bit of matter at a distance. There must be collisions. So this idea of action at a distance doesn't make any sense. So when Newton published his book, this was one of the major criticisms. They said, well, we like your mathematics, we like your calculations, and everything seems nice. But what about this weird notion of gravity as a force acting at a distance? What's the mechanical explanation of that? Essentially, for Cartesians, their notion of matter was the idea of mechanical matter. The matter is an extended substance interacting through collisions, and that's why their idea was action by contact. So to say that material objects can influence each other at a distance would be contradictory because it would be against their definition. For Cartesians, every material object is just an arrangement of material particles. It could be three different types of particles, but essentially they're all particles. The moon, the earth, the terrestrial vortex, the solar vortex, the sun, everything just colliding and combining particles. The moon revolves around the earth being pushed by the particles of the earth's vortex. The earth, along with its vortex, revolves around the sun being pushed by the solar vortex. So matter is inert. It does not have any inner forces. It doesn't have any capacities to affect some other bits of matter out there without actually touching. So it's inert. This is the notion of mechanical matter, inert matter. When we say mechanical matter or inert matter, this is what we mean, the Cartesian idea. So what would you do if you were a Newtonian in this situation? What would you do as a Newtonian?
Just taking a stab here, maybe I would change my definitions.
How would you change it?
Well, matter wouldn't be just a thing that's extended. It would have all these other properties, and one of them might be it has the property of having a gravitational attraction or something.
That's exactly what they did. It's a natural step to take. Change your definition of matter. If that's your major obstacle, then just remove it. And this is what they did. The notion of matter must be modified. And they came up with the idea of dynamical matter, which is the idea that matter is an extended substance interacting through forces. It is extension plus activity. It has an active beginning in itself. It can act on other bits of matter through forces. This is no longer your inert matter lazy boy chair. This is a lazy boy chair with a remote control now, you see? Every material object is composed of extended particles, right? It could be the Earth, the Moon. But extension is not the only attribute of matter. Have a look here. The bits of matter have a capacity of affecting each other through forces. So this is your Newtonian conception of matter. Extension plus activity plus forces. You see the difference here? One thing should be clarified, and this is very important when you study the history of science, to distinguish, separate Newton's position from the position of the community, the position of the Newtonians. And this can be generalized. When you study the history of science, very often you focus on the individual level, the level of individual scientists and their belief systems. This is very interesting if you are trying to write the intellectual biography of that particular scientist. But you have to separate, distinguish this from the opinion of the community. Individual great scientist is one thing, the community is quite often a different thing. Sometimes the views coincide, but very often, and we know this from the history of science, quite often their positions diverge considerably. And this is one of those situations. Now, for Newton himself, the idea of gravity acting at a distance was revolting. And he says this in 1693 in a letter to one of his friends. He says, "The idea of two bits of matter affecting each other at a distance is so foreign to me." And indeed, he tried to find a mechanical explanation for gravity. None of them worked. He wasn't happy with any of those solutions. But essentially, he was trying to find a mechanical explanation of gravity. So this whole thing is just an invention of the so-called Newtonians. Karl Marx once said, "If they are Marxists, then I am certainly not a Marxist." And we have to separate. When we say Newtonian, we mean the worldview accepted by the scientific community, not necessarily Newton's own. This is what became accepted, not only accepted on paper. You wouldn't normally come across encyclopedia articles that would say, "well, we accept dynamical conception of matter." No. This conception was actually implicit in many of the theories accepted at the time. We see that this is implicit in the theory of gravity, but it was also implicit in a whole bunch of different theories from different fields of science. Let's have a look. Chemical force. This was the accepted chemical theory of the time. The idea that substances combine due to inherent chemical affinities. The idea of a chemical force, or another name for this, is chemical affinity. So a combination of two substances is possible due to the presence of a chemical force. See, this is a new force. This is not gravity. This is an additional force that they try to impose upon matter. Here you have a table of affinities. Here's another table of affinities. Here's the top row. You have all different chemical elements. And here, vertically, you would have respective affinities. I'm going to explain. So here in this one, let's take silver, for instance. Silver is frequently alloyed with lead because of the respective affinity. They're very close to each other. Now let's take this one here, that's sulfur. Sulfur combines with iron better than it combines with gold because respective affinities have different degrees. So the chemical force is different. You see what they're trying to do? They're trying to imitate Newtonian physics. They're trying to explain chemical phenomena this time by applying the same template. You have different bits of matter and forces connecting them. And in this case, the force is not gravity, it's a chemical affinity. But you see the same idea, the dynamic conception of matter, matter interacting through forces? Let's take another one, magnetic force. Magnetic phenomena are due to an inherent magnetic force. Magnets attract and repel due to the inherent magnetic force. Like gravity, magnetic force acts at a distance. Here you see attraction of magnets due to the magnetic force, and here you see repulsion of magnets due to the magnetic force. The same idea. Two bits of matter, forces connecting them. This time you have another force, magnetic force.
What did Newtonians find wrong with the Cartesian explanations for magnetism and gravity that they decided, or that Newton decided to come up with another theory?
It's a very good question. The basic answer, and the short answer, they didn't work mathematically. It was a nice model in general, but Newton knew from the very beginning that the idea of vortices just cannot produce ellipses. It can give you circles. For planets, you need ellipses, right? You don't need circles. A vortex will give you circles. In his masterpiece, in his major work, Mathematical Principles of Natural Philosophy, 1687, Newton devotes a big chunk of space on refuting the theory of vortices by saying, well, it just doesn't make any sense. Empirically doesn't make any sense. So empirical considerations, that's the short answer. So you see how this is the same idea of dynamical matter? I'm going to give you one more example. This time is the vital force. The living matter is organized by an inherent vital force. Organic matter is endowed with and organized by a vital force. Here, we are material substances. There is nothing more to that, except for the soul. We're going to cover that. But as physical bodies, we are purely material. But this is not your mechanical Cartesian matter. This time, this is the dynamic matter, matter that is endowed with forces. This time, these are not magnetic forces, these are not gravitational forces. These are living forces. You see, the same idea penetrated into biology. There you have it, the conception of dynamical matter. It has to be said, there was very little agreement when it came to the actual list of forces that were supposed to be fundamental. So the argument was, okay, so how many forces are there? How many substantial forces are there? Can you actually reduce, let's say, the vital force to magnetism or to gravity? What is the list of forces? Safe to say that there was no agreement on the subject. But what they all accepted is that matter is capable of acting through forces, whatever those forces might be. Now, what about dualism? This is one of those rare occasions when they agreed with Cartesians. They actually share the same idea of dualism. Dualism is the idea that there are two substances, matter and mind. Again, with Descartes, we have matter, we have mind. For Descartes, there are purely material entities, inorganic, organic, and there are purely spiritual entities, angels and the Creator, and there are citizens of the two worlds, human beings. Newtonian dualism shares the same basic idea. Matter and mind, they can exist as separate substances. Now pay attention that we now deal with a different definition of matter. This time it's not just purely mechanical matter, this is the dynamic matter. But as far as the conception of dualism is concerned, it's the same thing. Okay? At the time, there's a huge debate as to where you should draw the line separating material from spiritual. Some would insist that all living things, all organisms, have inherent organizing principles which are essentially non-material, which are spiritual. So not only human beings have minds or souls or spirits, but also everything living would have the spirit. So this was one of the conceptions available on the market. It wasn't accepted, but it was available. There was a debate on that. Others would be, properly speaking, along the lines of Descartes, the initial suggestion that only human beings are citizens of two worlds. Yet others, like Lametri, for instance, they believed in something like this, that even human beings are purely material. They never denied the existence of God and angels. Laplace is one exception, but in general, it wasn't common to deny the existence of God. But there was a tradition to portray human beings as complete machines, that even the human mind results from a combination and collision of particles. So human beings would become machines. But what's important here, it would still be dualist, because you would still have two substances. You would have mind, not necessarily the human mind in this case, it would be angelic or divine, and then you would have your material substance. In any case, the accepted view was that there are two different substances, matter and mind. Very good. We know that hypothetical deductive method was also part of the Newtonian mosaic. We know that by the third law of scientific change, it must be a deductive consequence of the Newtonian theories. How was it a deductive consequence? This is your hypothetical deductive method. In order to understand how it followed from Newtonian theories, we have to go back to the dynamical conception of matter. Think of this. If matter is an extended substance interacting through forces, doesn't it really follow that such qualities as color, taste, smell, and other qualities, they have to result from a combination and interaction of matter and forces? You see, this is different from what Descartes had in mind, but the conclusion is very similar to the conclusion that Descartes arrived at. And it is similar because in both cases, fundamental qualities of matter do not include color, taste, smell. They do not include any of the sensible qualities. For both Descartes and Newton, color, taste, smell would be just a byproduct of something material affecting our senses. They're just byproducts. They are not inherent in matter itself. Can we all appreciate this? The same applies to the idea that any phenomenon can be produced by an infinite number of different combinations of interacting particles. Again, particles can interact through collisions or through forces in this particular case, but it doesn't change the major idea that they have to interact somehow, and any phenomenon is a result of this interaction. And this brings us to the two basic principles, the idea of complexity and the idea of post hoc explanations. Once you arrive at this, you arrive at the principle of complexity, that the world as it appears in observation is a product of some more fundamental inner mechanism. And similarly here, the moment you appreciate this, you'll arrive at the idea that any phenomenon can be given many different post hoc explanations which are equally precise. The moment you appreciate that, you have to do something with your method. So what do you do with your method? There's a natural solution to this. These two would be your theoretical assumptions, and your method by the third law would be hypothetical deductive, which is it's okay to try to guess the internal structure of things. Despite the fact that Newton hated hypotheses. You see, this is very ironic. Newtonian science was all hypothetical deductive. If you look at the theories accepted at the time, chemical forces, vital forces, magnetic forces, what are these forces? They're hypotheses. You never observe those forces, do you? The force of gravity itself is a hypothesis, isn't it? You don't observe it. What you observe is a change in position. Force of gravity is a hypothesis, so it's not really surprising that Newtonian science was hypothetical deductive, despite the fact that Newton himself didn't really like it. Max?
Why we have to justify why the Newtonian worldview deduces the HD method, because wasn't the Newtonian theory of gravity accepted because it was more accurate, so it wasn't therefore accepted through the HD method?
This deduction is only important for those communities who transitioned from the Aristotelian to Newtonian immediately.
Okay.
So in France, the first 40 years of the 18th century, from the 1700 all the way to the 1740, they were Cartesian, right? We know this. And in that community, hypothetical deductive method, it had been employed before the acceptance of the Newtonian worldview. So there was no transition in method there. It was the same method. And Newtonian, as Max rightly pointed out, Newtonian theory was accepted because it satisfied the requirements of the hypothetical deductive method. You remember those two expeditions, Lapland and Ecuador, Peru. But for the communities that transition immediately from Aristotelian to Newtonian, this would be most of England, really, Oxford, other places. They didn't have a Cartesian stage in between. Cambridge had, but most of England, they didn't have a Cartesian stage in between. For those, this is how they arrived at the hypothetical deductivism. Does this make sense? That's very good. Let's sum it up. Now you tell me here. We have pluralism here, and here we have what? Dualism. Here we have teleology, and here you have action by contact and action at a distance. Here you have hylomorphism was replaced by, yes, mechanicism, and here you have a conception of dynamism or dynamic conception of matter. And finally you have the Aristotelian method, and then you have HD here. If you pay attention, the transition from Aristotle to Descartes was more drastic than that from Descartes to Newton. Almost everything was different. This gives you a sense of the scope of the transition. That is one of the reasons why when we say the scientific revolution, most of the time we refer to this transition towards the end of the 17th century. There is a reason why we say the scientific revolution. And the major reason being the difference in methods, the transition from the Aristotelian medieval to HD. As we're going to see next week, we still employ the hypothetical deductive method. So as far as method is concerned, at the fundamental level, we share that method with the Newtonians, with Cartesians, and this here was probably the most drastic change in the history of science. Make sense? Very good then. Next time is the contemporary worldview. And now, thank you very much.